Hello, this is the Code Critics. In this episode we are going to look at recursion. If recursion confuses you or you don't know when to use it, this is for you. But you still will be confused. Let us ease into the topic by looking at some very simple recursive functions. This function named zeros prints the number 0 and then calls itself again. That is the recursion. What does it do? It prints 0, then calls zeros, which prints the number 0, then calls zeros again, which you get the idea. In theory, this loop goes on forever. In practice, after 1000 iterations, you will see a recursion error occurring with the message maximum recursion depth exceeded. The reason is that when Python calls a function, it reserves a special piece of memory called the stack. A function is removed from the stack when it is finished, but the zeros function never finishes. By calling itself recursively, it places more and more copies of itself on the stack until the stack overflows. Generally, we need an end or base condition to stop this infinite loop. A common method is to add a counter variable that is decremented each time the function is called. In the following extended implementation of zeros, we provide the counter variable n, which is decremented in the recursive call. If n becomes smaller or equal to 0, we return and the recursion ends. This means the topmost zeros function on the stack is finished and will be removed, which means the second topmost zeros function is finished as well and will be removed, and so on until all zero functions are completed and the stack is empty. In most cases, we want functions not to print something, but to return a value or a data structure. How does this work with recursive functions? Let us change the zeros function to return a list of n zeros instead of printing it. The end condition is almost the same, but we return an empty list. The recursive call, however, looks interesting. We return a list with 1 0 in it and add or append the list that it is returned by calling zeros for n-1. That means we are creating a list with n items by creating a list with 1 item and then appending a list with n minus items, which itself is created by creating a list with n minus 2 items, and so on until we add the empty list. Instead of only creating lists with zeros, we can easily generalize the recursive function to create lists of arbitrary items. Here the implementation of a function makeList, mklist, that allows that. Now we can call mklist and create a list of a's, for instance. Let us step back a little and identify the two essential components of recursion. First, there has to be a self-similar, self-replicating pattern. In the case of makeList, it is a fact that a list with n items is defined as a list with 1 item plus a list with n minus 1 items. Second, generally an end or base condition is required to stop the recursion from running infinitely. In case of makeList, we stop when n reaches 0. Makelist and the other examples are just that, examples. Instead of recursion, we could have just used for loops or list comprehensions, and it would have been a better solution. There are, however, cases where recursive solutions shine, and that is for tree or graph structured data. Here we have a tiny phylogenetic tree, represented as a nested list of lists with species names as strings. A phylogenetic tree describes the relationships between species, and we could draw it as a tree. Now we see that humans evolutionary are closer to chimpanzees than gorillas, for instance. Clade is any subtree of a phylogenetic tree, including itself. How can we print all the clades of this phylogenetic tree? Since trees are composed of subtrees and are self-similar, a recursive solution seems appropriate. The function printClades takes a tree and first checks if it is a list. That is our end condition. If that is the case, we print the tree and then iterate over all the subtrees and recursively call print clades again. If you play this out in your mind, you will find that the recursion walks down the left-hand side of the tree first, while printing the clades in decreasing size. This is called a depth-first recursion. Note that the recursive implementation is a very short, readable and intuitive description of the process. We print all clades of a tree by printing the tree and all the subtrees. By the way, if we move the print statement after the for loop, the code would print the clades in increasing size instead of decreasing size. What if we want to print the species names only? That is easily done as well. The function print_species is almost identical to print clades, with the only difference that the print statement now sits in an else branch, which means we are only printing if the tree is not a list, which means it has to be a string with a species name. Final example. A common question to ask is how old a species is in evolutionary terms. Within a phylogenetic tree, this means how far from the tree root the species names appear. For instance, gorilla is 3 branches away, while gibbon is only 1 branch away and therefore evolutionary older. The recursive function depth returns the level of a species name within the tree. First, it checks if the tree is equal to the species name. If so, it returns the level. If not, it iterates over the subtrees and recursively calls depth with an increased level. All these recursive calls for the subtrees return a level, which is either -1 if the species was not found, or it is the level of the species. We therefore return the maximum of these levels. The last line in the code covers the case when the species was not found in a specific subtree. Recursive solutions can be very compact and elegant, but also inefficient. We will have a look at the trade-offs between recursive, iterative, and other solutions next. The Fibonacci numbers are a classical example of recursion, since they are defined recursively. The Fibonacci number f of n is 0 if n is 0, and it is 1 if n is 1. Those are the base conditions of the recursive definition. The self-similar recursive part is next, where f of n is defined as f of n-1 plus f of n-2. A recursive implementation of this formula in Python is very simple and straightforward. If we call fib_r, r for recursive, for numbers of n from 0 to 9, we can print the Fibonacci series with 0, 1, 1, 2, 3, 5, and so on. This implementation is, however, very inefficient and very slow for slightly larger n. Computation for an n of 40 already takes multiple seconds. The reason is that there is many duplicate computations occurring. For instance, fib_r of n-1 and fib_r of n-2 are both computing the same sequence of Fibonacci numbers twice, with the exception of the last. An alternative and much more efficient solution is an iterative implementation. Here it is. Variables a and b are initialized with base cases, and then we have a simple for loop that updates a and b, following the Fibonacci definition. Thanks to Python's tuple unpacking, this can be done very elegantly without the need of a temporary variable. The problem with the iterative solution is that, in contrast to the recursive solution, it is not obvious how to get there. Especially for more complex problems that are recursive in nature, this tends to be difficult. Luckily, there is an easy way to speed up a recursive solution that suffers from duplicate computations. The technique is called memoization and simply caches all computations. Here an implementation for the Fibonacci numbers. Initialize the cache with the base conditions, and for any n we get, we first check if it is in the cache. If so, we retrieve the value stored in the cache and return it. If not, we compute the Fibonacci number, put in the cache and return it. This recursive solution with caching is as straightforward to implement as the purely recursive solution. And it is essentially as fast as the iterative solution. Both have the same computational complexity. However, it requires more memory, since it stores all computed Fibonacci numbers in the cache. In the case of the Fibonacci numbers, there's actually a closed form solution for their computation. The implementation is simple, and in most cases the preferred method. Let us summarize. Recursion is characterized by a self-similar, self-replicating pattern, and typically needs a base or end condition to avoid infinite recursion. It is tricky to get right, but results in very compact and simple code for problems that are recursive in nature. The main applications are trees and graphs, such as phylogenetic trees, syntax structures, ontologies, and many more. Recursive solutions can be slow, but caching of results using memoization is often a simple way around this problem. Finally, stack overflows due to many recursions can be an issue. However, Python has the function setRecursionLimit to set the maximum recursion depth. And that's it. Thank you for listening.